Hello. In this video, we will discuss dynamics of uniform circular motion. So, by dynamics, we mean forces and how forces affect the motion. And uniform circular motion, the word uniform here refers to the constant speed motion. So, we look at constant speed motion in a circle. Say we have a circular motion, something's going in circle. Maybe you're driving a car in a circle, or you have a thread and a stone, and you're spinning the stone around in a circle. Whatever, there's something going in a circle, and so it's a different place, but it's covering the same distance in the same amount of time. So the constant speed, and in the center, and you know that in this case the acceleration at any instant, say t1, a1 will be pointed towards that, and acceleration at t2 will be in this direction. So t3, the acceleration will be always point towards the center in the same magnitude. And since the speed is constant, we just use a single letter v is the speed, constant speed. And so here acceleration 1 here, acceleration 2 here, acceleration 3 here. All these accelerations have a constant magnitude of acceleration, which is a net acceleration. There's no other acceleration in uniform circular motion, and that is equal to v square. If the radius of the circle is r, then it's v square over r. So, and we sometimes give a different symbol for this. We say this is a sub c, and we call it centripetal acceleration. From Newton's third law, sorry, Newton's second law, not third law, second law, we had earlier noted that net of all forces, so net, and we have external forces, external to whatever is moving, so net external forces, you can decorate all of these extra properties, is mass of the object times the acceleration, which is the net acceleration. So this is the law at each instant. And this is the law for mass is fixed, mass not changing. So suppose if we are studying the motion of a car around a circle, motion of the car is fixed. So here, how do we apply this law? Well, this may consist of sum of all the forces. Suppose you have like two forces, then you have if two forces, then you add them in a vector way. Like x component of this will be the sum of the x component of this, and y component of this will be the sum of the y component of this. This you know already. And you have other forces, then you have to add as many forces there are. So that's what this means. So when we look at a circular motion, we need to look at one instant. So let's look at a circular motion. And so say I'm looking at a car that's going in a circular path. It might go all the way around or just go part of the way around. But as long as it's a part of a circle, we can look at, we can examine it this way. Okay. So here you can see that at this instant, you can say this is my x direction. If I say this is my positive x direction, then sum of f net x will be mass times v square over r. So this is acceleration. This will be ax and this will be net x. So we need to be able to add all the forces over here. If this is x direction and if this is the y direction, then if I look at all the y's, that should add up to 0 because there's no acceleration along this direction. Then there is if you use a right hand rule, the z direction, z axis is pointed up. So z pointed up. We pointed up direction we indicate by a tip of an arrow, as if the arrow is shooting straight up. And if I look at the forces along this direction, they should add up to 0 because there's no acceleration there. This is the only acceleration. This is the acceleration. So there is no acceleration along this direction or along the z direction. So these are three equations we're going to get when we apply Newton's second law to circular motion with a uniform speed. So let's look at an example. Say a car is going in the bend. So the car uniformly rounding a bend. So we're looking from the top view. So here is the origin at the center, or this is the center, and we just will use this as an x-axis for the sake of simplicity. That's so you can say the place where the car is the origin for now, and this you can be y, and this is the z. So if you look at it, what are the forces on the car? Well, the earth is so if this was the z-axis, let's see, the z-axis is this way, this is the z-axis. So this z-axis. If you look at that, weight of the car is along the z-axis. And there's a normal from the road along the z-axis. This is what's happening along the z-axis. There's no weight is. Of course, the engine is part of the car, so it's not external to the car. You might say engine is applying force. No, engine is not applying force on the car, as we note here as external force on the car. So, what are the other forces that's responsible for it having acceleration this way? If you look at very closely, you'll say if there was no friction between the tires of the car, the car couldn't round the bend. That means if I look along the x-axis, so this is along the x-axis, there is a static friction on the car. And there's no other force here. So this is what's happening along the x-axis. How about the y-axis? Well, along the y-axis, if I look at along the y-axis, the car is, say, moving that way, so the velocity is that way. This is the direction of the velocity. So there must be the wind applying that way. So that there's a drag force on the car that way. And of course, if there's only force, there will be acceleration here. So there must be another force that way. And that's the rolling friction from the road onto the car. So we can say rolling friction. So this is the situation along the y-axis, and the y-axis is that way. So what do we get in the car? If the speed here is v and the distance here is r, then here we will get one equation along the x-axis, which is F sub s equals mass of the car, speed of the car. So that's one equation. Second equation along the y-axis will be the drag must equal to the rolling friction. F drag minus F rolling must equal to 0 with no acceleration here, no acceleration component. along this axis. And then we're going to get, if I look along the z-axis direction, we get Fn minus W equal to 0. And if you are working with this maximum static friction, then this may be a maximum, and then there's a relation between Fn and Fs. So if we are working at maximum Fs, like Fs max, then we'll have a mu sub s Fn. Also, we'll have this fourth equation only when working with the maximum static friction. Otherwise, we just have these three equations. And this should be sufficient to solve problems regarding what we need to turn a corner in a car with certain amount of static friction that's possible. So I'm going to stop here, and next we're going to talk about dynamics in the case when we don't have uniform circular motion. So the next up is dynamics of non-uniform motion, circular motion. And this was the case when you, for instance, in a pendulum, you're going up and down. So if the speed is 0 here, v is 0 here, but then speed picks up, and over here is a high speed and then slows down, and 0 again here. So the speed is varying, but the whole thing is moving in a circle. Another place that you can see non-uniform circular motion is when you say this is a Ferris wheel. Well, when you start out the Ferris wheel, you have no speed, but then at some point you pick up speed, and as you're going, maybe after that you're getting uniform. But from here to here, it's a non-uniform motion. So there's these cases we're going to talk about next. So see you in the next video.